So today we're gonna talk about beats. Now you may think Beats by Dre. Well, that actually has to do with Beats by Physics. Now this picture over here you can see got from this website, and you can see that there's all these. There's a wave, right? There's a wave here, and there's actually two of them. There's wave Y1 and wave 2. And what's gonna happen is, as you learn in this video, that these two waves actually combine to create a envelope wave, which is this green line over here. And the point where there's going to be destructive and constructive waves as well. So we're going to continue. So, what are beats? Well, in the textbook, they also say is a variation of the amplitudes. So there's the beat F force of the beat, which is represented by the frequency 2 minus the frequency 1 is equal to frequency of beat. Sorry, I meant frequency, not force. And what this equation means is the difference in the frequencies, so the frequencies, give a rise to a beat. However, there's an exception. If the frequency is very large, then we hear two distinct tones and one tone that varies in intensity. So, for example, you're whispering and you also have someone being in a jackhammer. Well, you're gonna hear two distinct tones. Maybe you can hear a little bit of the whispering and the jackhammer, not, you know, uh, than one tone that has a different intensity. If I hope you understand what I mean by that. It can be two very loud things. So before I move on to talk about more about beats and all that, we need to really understand what interference is. So there's two types of interference: destructive and constructive. Now you can think of destructive as you're being destructive, and it the two destructive waves kind of cancel each other out. So we got two bad kids, destructive, and constructive. They're constructively helping each other out. So constructively, they're helping each other out to make one, larger wave. So how are beats caused? Well, beats are actually the interference of two waves in the same point in space. Same point. So we got this point and that point makes this bigger point here, and this point and that point makes that point here. So you can see, I'm going to quiz you. What is this? Is it constructive or deconstructive? Give you a second, pause that video, go back to my other slide, and you get to probably think that through. So, combined wave envelope. So as you might have saw my first slide over there, a combined wave. So in phase, what we're gonna have. So this is in phase right here. This is out of phase. So this is the phase. We're talking about this phase only. So at the end of this phase, the two waves are destructive here, and over here, this is just a resulting of two waves. And I'm going to show you how you can actually kind of figure this out equationally. I'm just trying to give you a graphical process here. So where's the math, you might be wondering. So I actually chose a different form of equations that you might help out. I also found the equation in the book to be a little bit stressful. So these are the same equations that are in our textbook, equation 1522 and 1523. So you got to choose a phase first. So phase pi 3 that shows that. Then what you have here is this wave equation 1 is given by this formula. So identity here, sine identity, cosine identity. And you also got phase, also got another wave here, y2. So what we're going to do is that, as you may remember from this slide, it's constructive or deconstructive. What we're doing is this is y1, this is y2. Well, that's what we're trying to say. And by saying that, what we're actually doing is we're just going to add these two. So by adding these two, this is what we're going to get. Okay, we're also assuming kind of the same amplitude. So by adding these two, we're gonna, add these two, take the a as a common factor out, and then we're gonna add these two together. And then we also can refer back to our trig identity that this is exactly the same as this. You might want to look back and refer to your calculus textbook or something like that. And then this is actually the equation that results from both of these, where we're actually just subbing these in here. We get this. So there's another equation to consider. So the y envelope. So as I mentioned before, the envelope was basically this. This is the envelope here. It looks kind of like an envelope, maybe an eye or something. And that y envelope equation is given by 2a cos 2 pi, frequency of 1, minus frequency divided by 2 times time. So if you were to calculate what the y envelope was, what you have to do is you got to look back to your other formula. You figure out your givens and plug it in your y envelope. And also as well, you might be wondering, well, what's my angular frequency? And how do I find the angular frequency difference? Well, it's given by these two equations here and here. My equation format for Microsoft Word wasn't working, so I had to apologies for the nasty looking equations over there, but that's what it's like. You can also refer to equation 1524 in your textbook. Also gives you those. So I want you to, figure out I hope you understood the concept, right? And this, I forgot to mention that this actually represents the amplitude, also the intensity of the sound. So, we discussed what beats were, and we also, this gives the intensity of the sound. So here's some questions. Don't get too tricked with this. It's fairly simple. Fairly simple question you should be able to get. And I want you to tell me what this actually represents. And also equation to conceptual questions. So in my previous question over here, I want you to, pause this video or something and then pause my other slide. So what would you do if you had different amplitudes? And what would you do if you had different times? And what would you do if there are two different frequencies that weren't given? Okay, so, and I'm gonna give you a little second to work on that. I'm gonna go to my next answer slide. And answer the first one is this, and this represents what I mentioned over here, my amplitude, also the intensity of the sound. So, this is the envelope wave, represents the amplitude of the envelope. So the green little line there, and if you see that properly, the green line there. And also the equations of what do you do if you had different amplitudes? Well, what you would do is you would actually um, figure these amplitudes up by subbing the two equations together. And from that, you'd have to figure out a ratio of the amplitudes. You'd have to relate the amplitudes somehow, in some way, in order to figure out the to make sure you have the same frequency. And what would you do if you had different times? Well, we were talking about this to be at the same time, so you'd have to have the same time if it wouldn't work. What would you do if you had different frequencies that weren't given? Well, in that case, you'd have to figure the frequencies out from the different givens that you see over here. So if you had, you had this, and you had your time, you'd have to figure out your frequency for one equation, figure out your frequency for the other equation, and then use the formula over here to figure it out. You also had to have the same amplitude there. So I hope that helps.